Now we are discussing about when two bodies are in contact, as we are having a transfer of heat takes place from one body to another body, then what happens about the temperature there, that we will see between the two bodies. Okay? This we call that as principle of calorimetry. Okay? Principle of calorimetry, or it is also called principle of mixtures. Okay? Principle of calorimetry, or it is also called principle of mixtures, that is. So, in this principle of calorimetry means, if you are taking any two bodies having different in the temperature there, means I am taking a hot body and I am taking a cold body. When this hot body and cold body both are in contact or both are mixed, like liquids you can take, or hot water, cold water you can take. If both are mixed, what happens there is a transfer of heat takes place, as you know, from hot body to cold body, means high temperature body to low temperature body, that is. Now, after some time, according to that thermal equilibrium, here both the bodies are coming to the same temperature, okay, of which that is our common temperature or final temperature, where there is a stage where the flow of heat energy transfer takes place, stops, and that only we call that as thermal equilibrium. Now, by using this principle of calorimetry, now we are finding the final temperature. At first, if you see the statement of principle of calorimetry, when two bodies are in contact, and make sure that two bodies are having different temperatures we are taking, both are having different temperatures. When two bodies are in contact, then heat flows from hot body to cold body, hot body to cold body. Then during this transfer of heat, what happens there is amount of heat energy loss, amount of heat lost by the hot body, because it is giving out the heat, means the temperature change for the case of hot body is decreasing we have. Okay? So, there is a fall in temperature for the case of hot body here. So, the amount of heat lost by the hot body is equal to amount of heat energy gain, amount of heat energy gain by the cold body. Okay? So, this is the statement. Okay, see that again. So, the amount of heat lost by the hot body is equal to amount of heat gained by the cold body, that is. So, as it is losing the heat, there is a fall in temperature for hot body. As here it is gaining the heat, there is a raise in temperature for the cold body here. And both are coming to one final temperature. Okay, that only we call that as a common temperature. Okay, where there is no further transfer of heat takes place between them. Okay, this principle we call that as principle of calorimetry, that is, where heat lost by the hot body is equal to heat gained by the cold body, that is. Actually, here if you observe, it is nothing but the consequence of conservation of energy, that is, nothing but conservation of energy, that is. Actually, it is not a new statement for you. You already know about conservation of energy. Because here hot body is losing the heat energy, means here that heat energy it is not destroying there. At the same time, the cold body is gaining the heat, so which means that is not created. Whatever the heat lost by the hot body, that heat energy only gained by the cold body, which is nothing but our conservation of energy statement. Energy neither be created nor be destroyed, but we can transfer that energy from one to another. You can transform the energy, or you can transfer that energy from one to another here. Here, if you are taking the two bodies there, hot body and cold body, hot body is giving its heat energy to the cold body. So, that is why principle of calorimetry is nothing but the consequence of the conservation of energy we are taking. Okay. So, mathematically if you are taking this principle of calorimetry, Okay, mathematical relation if you are taking, let us suppose I am having two bodies, let it be that is of A and B, and I am taking A is the hot body and B is the cold body, that is. So, A is hot body, B is cold body, that is. Okay. Now, hot body means its temperature is more, let it be the temperature of hot body is TH. TH represents temperature of hot body, that is. Okay. You better note that. Temperature of hot body, TH. Temperature of hot body. Okay. Now, come to the next case, which is of cold body. Cold body, let it be having the temperature TC. Okay. So, TC, temperature of cold body. Okay. Now, here as the temperature of hot body we are taking means TH is more and TC is less, means temperature of A is greater than temperature of B. This is the condition we are taking. Now, here as both the bodies A and B are in contact, then what happens there is heat is flowing from A towards B, that is. So, heat energy flows from hot body to cold body. As the heat energy is flowing from hot body to cold body, that hot body is losing the heat energy. There is a loss of heat energy here for the hot body. Then what happens there is its temperature decreases, that is due to that. Okay. And at the same time other side we are having the cold body. That cold body is gaining the heat, Q gain. So, there is an increase in the temperature for cold body here. Okay. Hot body is losing the heat energy, cold body is gaining the heat energy. Q loss is equal to Q gain. This process takes place until both are getting the thermal equilibrium here. Once they got this thermal equilibrium, then there is no further change of temperatures here. Means there is no flow of heat from A to B. Okay, because that is in thermal equilibrium, that is. Then at that case the temperature TH and the temperature TC both are coming to one common temperature, let it be that is T. Okay. So, T is the common temperature we are having. Okay. Then as Q loss is equal to Q gain, as whatever the heat energy losing by the hot body, let it be that is of Sm delta T we are taking. Sm delta T. This is for hot body. And Q gain, which is of Sm delta T for cold body we are taking. Okay. And remember in this case, now for this example, now we are not taking any change of states. Change of states later we will see. Okay. Without change of state, only about change of temperatures only we will see here. Okay. Then Sm delta T of hot body is equal to Sm delta T of cold body, that is. Then S means the specific heat of hot body, M means mass of the hot body, and delta T, which is the change in temperature. Actually initial temperature is TH, final temperature is T. So, that is why as it is decreasing, TH is more and T is less. T means our common temperature. Okay. That is why here the change in temperature becomes TH minus T, that is. Okay. So, TH minus T, that is equal to specific heat of cold body and mass of cold body, and delta T for cold body means actually cold body temperature is less, now it is rising, yes, and it is raised to T here. So, that is why here now the T is more and TC is less, the change in temperature becomes T minus TC. Okay. So, this is the final formula we got, of which specific heat of hot body into its mass into change in temperature TH minus T is equal to specific heat of cold body and mass of cold body into T minus TC, that is, which is of change of temperature. Okay. This is called principle of calorimetry. For suppose if you are taking both the bodies are of having same specific heats you are taking, for example hot water mixed with cold water, means specific heat of water remains the same in both the cases. Means I am taking a special case, if SH is equal to SC, then specific heat of hot body is equal to specific heat of cold body, that is. Then if you are taking specific heat of hot body equal to specific heat of cold body, let it be that is equal to S. Then S into mH into delta T, which is TH minus T, okay, and that is equal to specific heat S of mass of cold body into T minus Tc, that is, okay. Then here S and here also S, both the S get cancel, and we got mass of hot body of TH minus T is equal to mass of cold body of T minus Tc. This is the case, okay. So mass of hot body into TH minus T is equal to mass of cold body into T minus Tc, that is, if you are taking in both the cases the specific heats are same. Actually what we need is the final temperature we want. So that's why here I am taking the final temperature, which is of mH into TH, mH minus mHT is equal to mC into T, mCT minus mCTC. Okay, bring all final temperature T to one side, then it becomes mC coming this side and mH the going that side, then mHTH minus mCTC coming this side becomes plus mCTC is equal to mHT going that side, it becomes plus mCT mHT, that is. Finally what we need is that common temperature T we want, then mHTH plus mCTC is equal to T of, if you take T common, mC plus mH, then finally T is equal to, bring this mC plus mH this side, then it becomes mHTH plus mCTC by mC plus mH. This is the formula, okay. When if you are taking the condition, if SH is equal to SC is equal to S there, then this is the case, okay. Have understood now? So the use of this principle of calorimetry is, finally we are getting what is the final temperature or the common temperature we are getting when the two bodies are in thermal equilibrium, when they are in contact. If suppose if the specific heats are not equal, means both we are taking it as a two different one, then how to take that is, final temperature T becomes SH mH TH plus SC MC TC by SC MC plus SH MH. This is the direct formula, okay. SH MH TH plus SC MC TC by SC MC plus SH MH. That is the final formula we have. So finally we got T is equal to SH MH TH plus SC MC TC by SC MC plus SH MH. Then what is the use of this formula? Okay, see here we got T is equal to final temperature SH mH TH plus SC MC TC by SH mH plus SC MC, that is. This is the final temperature formula, okay. Now if you see a numerical example on this principle of calorimetry, then I am taking a simple case there, so that I am taking both cases having same specific heat case, okay. Means I am mixing hot water with cold water, that is, okay. For example like this, if 20 grams of water at 80 degrees Celsius is mixed with 80 grams of water at 20 degrees Celsius, okay. So 20 grams of water at 80 degrees Celsius is mixed with 80 grams of water at 20 degrees Celsius. Then find the final temperature. Okay, like this. Then in this case, as we both are having that specific heat of water only present, which is of 1 calorie per gram degree Celsius, we can cancel that S here. Then if you follow the steps, we know that Q loss is equal to Q gain, that is. Then if Q loss is equal to Q gain, Q loss means Sm delta T of hot body is equal to Sm delta T of cold body, that is. Okay. Then as it is of specific heat of water, which is of value is 1, and mass of that body, which is of for hot body, mass is of 20 grams. And for change of temperature here, actually initial temperature is 80 and we don't know how much is the final temperature, means TH minus T, 80 minus T is equal to, this is for hot body. Now for cold body, again we are taking for water only, specific heat is 1, whereas mass you are taking, that is of 80 grams is there, 80 into change of temperature, which is initially that is of 20 and it is rising, means final temperature is more and 20 degrees Celsius is less, that is. So that's why here we have to take T minus 20, that is. Then 21s and 24s get cancelled, here you will get 80 minus T is equal to 4 into T, 40 minus 4 into 20, 80, that is. Okay. So then if you bring that minus 80 this side and T that side, then you will get, bring that 80 this side, 80 plus 80 is equal to minus T coming that side becomes plus T, plus T. So 4T plus T, 5T is equal to 80 plus 80, 160, that is. Then T is equal to 160 by 5, which is of 32 degrees Celsius. If you observe in this example, actually our hot body is at a temperature 80 degrees Celsius. Hot body temperature, which is 80 degrees Celsius. And cold body temperature, if you see, which is of 20 degrees Celsius, that is. This is of 20 degrees Celsius, which is Tc. Then our temperature, final temperature, which is of 32 degrees Celsius, it is in between this hot body and cold body temperature, which means that whenever if there is a thermal equilibrium comes in between the two bodies of hot body and cold body, always that final temperature, most of the cases, it is less than the hot body here. Okay, means always hot body only has to be more. Okay, and very special cases they may be equal also, you can take. TH is greater than or equal to T. And not only that, when come to the case of cold body, here our final temperature, as the cold body is receiving the heat, it never falls temperature there. Always we are having a increase in temperature, or sometimes it may be same only remains there. Okay, then in those cases cold body has to be always less, that is, means final temperature only more always. And very special cases we are having that may be equal to that one, like this. Okay, so that's why we got here TH is always greater than or equal to T and greater than or equal to Tc, that is. Okay, in our problem we got here 80 degrees Celsius, which is more when compared to 32, and 32 degrees Celsius is more when compared to 20 degrees Celsius. So that is the limit here for the T value. It never be more than TH, it never be less than Tc. T never be less than Tc and T never be more than TH. Okay, it won't happen. Okay, T never be less than Tc and T never be more than TH, that is. Okay, in this way we can solve for the case of principle of calorimetry and we can get the final temperature, and we are taking the case where for the case of same specific heat capacity for hot water and in the case of cold water, that is. Now, after this specific heat capacity and the principle of calorimetry, now we are seeing another important one, which is called latent heat capacity. Okay, latent heat capacity represent with L. Okay, so we already know about specific heat capacity there, amount of heat energy required to raise its temperature by 1 degree Celsius by unit mass of a substance. Now we are taking latent heat capacity. Remember, while discussing about the specific heat capacity, as I said, when there is a heat energy is supplied to any of the substance, depending on the nature of the substance, that heat energy is utilized in a different ways, I said. When there is a average kinetic energy is increasing, then we are getting the change of temperatures there. Now we are seeing there are no rise of temperatures here in case of latent heat capacity. Means unless using that heat energy for increasing its kinetic energy, now the substance is utilizing the heat energy for some other purpose, that only the change of state. So latent heat capacity comes when there is a change of state is present, change of state of the substance. Means here the heat energy given is utilized not for the case of increasing average kinetic energy, it is utilized for changing its potential energy here. Okay, changing its potential energy means as the molecules in case of say for example solid, if you are taking, the molecules positions are very much closer to each other, that is, all are very much closer to each other. But whenever if you are supplying the heat, say for example in case of ice, if you supply heat energy to the ice, we know it starts melting. Then the molecules which when in case of the ice if you are taking, those are very much closer to each other. We are having a fixed potential energy for that. But once you start heating that one, slowly the ice start melting there. Means the distance between the molecules is changing here, so that the potential energy also changes. And in the same way in case of water you took, if you are supplying heat energy more and more to the water there, slowly it starts vaporizing. Means the molecular distances is increasing here, so that the potential energy varies from point to point depending on the heat energy we are supplying. So here during the change of states, there are no temperature changes occur. Very, very important one. There is no change of temperature if there is a change of state takes place, because during the change of state, that substance is not utilizing the heat energy for increasing its temperature. It is utilized for some other purpose. As the kinetic energy is not changing, that's why the temperature is also not changing. So that's why the delta T value is 0. Which means T is equal to always constant here. Okay. Now what is this latent heat capacity means? Latent heat capacity is also like a specific heat capacity, which is the amount of heat energy required or given out by unit mass of a substance, this time not for raising its temperature, it is for change of state. Okay. So and the formula for this latent heat is L is equal to Q by M, that is L is equal to Q by M. L equal to Q by M means here if suppose if you are taking mass as unit, M is equal to 1, means for a unit mass of a substance, whatever the amount of heat energy required Q is nothing but called as latent heat capacity to change its state, to change its state. Okay. So see that again the definition, the amount of heat energy, the amount of heat required or given out, required or given out by unit mass of a substance, unit mass of a substance to change its state, to change its state is called latent heat capacity. But remember, at a constant temperature only it takes place. Okay? At a constant temperature. At constant temperature here, the amount of heat energy required or given out by unit mass of a substance to change its state, that heat energy only we call that as the latent heat capacity, that is. Okay? What is it called? Latent heat capacity, that is. Then as latent heat capacity, L is equal to Q by M. Then if you come to the case of units, then its CGS units becomes, which is of Q, it is of calories, mass it is of grams. Whereas SI system, if you are taking, calorie becomes joule, gram becomes kilograms, that is. Calorie per gram, joules per kg, that is. Okay? Now, this is the unit of latent heat capacity. And if you are taking an example, okay, actually we are having change of states, many change of states we have. Now, we are taking according to our repeated questions there, okay, or about our entrance exam, we are having mainly 4 change of states we have. One is from solid to liquid, solid to liquid. In this case, actually we have to supply the heat energy here. Okay? We have to supply the heat energy plus Q, that is. This method we call that as melting or fusion, FUSION. Okay? Conversion of solid to liquid, that is. Here we need the heat energy. Okay? Solid to liquid case. And if you are taking from liquid to gas, this one we call that as boiling or vaporization. It is also called as vaporization, boiling or vaporization. Here also we want supplying the heat energy here. We have to supply heat energy to the liquid so that it becomes gas. And the next one we are having the reverse case, of which while giving out the heat energy means gas, it is converting back into the liquid here by giving out the heat energy. So, which is of minus Q. This process we call that as condensation, converting from gas to liquid, vapor to water. And next one, liquid to solid case. In this case also, again it is giving out the heat energy back to there, and so that it is becoming solid. This we call that as freezing, because there is a fall in temperature present. So, in case of freezing and condensation here, it is giving out the heat energy, and in case of fusion and boiling or melting or vaporization, it takes the heat energy. But if you observe here, solid to liquid and liquid to solid, as the same substance it is taking the heat while going from solid to liquid, and the same substance liquid now while coming back to solid, it gives out heat energy. And particularly here, the amount of heat energy it is taking while becoming solid to liquid, the same amount of energy it gives back whenever it is converting from liquid to solid, from conservation of energy, that is. And in the same way, when it is going from liquid to gas, actually it requires heat energy there. So, that is of, let it be Q2. Now, while coming back means gas is now becoming liquid by giving out the heat energy, then it becomes again the same amount of heat energy, whatever it takes, the same amount of heat energy it is giving back here, that is of minus Q2, that is. Okay. So, Q1 how much it is taking, and minus Q1 how much it is giving back. Again Q2 how much it is taking, and Q2 is amount of heat energy given out during condensation process. Okay. So, based on these 4 change of states, we are having mainly 2 latent heats are present. One is of the latent heat of fusion, if it is taking the heat energy or if it is giving out the heat energy, as both are same. So, for both the process of melting and freezing, we are taking the same latent heat, which is called latent heat of fusion, that we call that as latent heat of fusion, FUSION. Okay. Whereas, if it is going from liquid to gas, we call that as boiling or vaporization, or in the reverse process while giving out the heat, which call that as condensation. For these 2 cases, we are having the same latent heat we are taking, which is of latent heat of vaporization, latent heat of vaporization, that is latent heat of fusion, latent heat of vaporization. Remember, this latent heat of fusion or freezing, this takes place at its melting point, because I said the temperature remains constant. So that's why latent heat of fusion here, this is at melting point, that is. And whereas this liquid to gas, that only called as boiling point or condensation point, which means in reverse case, that is. So it takes place only at a constant temperature of boiling point we are taking. At boiling point, that is latent heat of fusion, latent heat of vaporization, that is. Okay. So these are the two we are having in case of latent heat capacity, that is. Depending on the change of state, the amount of heat energy required there also changes. Okay. Now if you see the definition of latent heat of fusion, it is the same like latent heat capacity, that is, which means whatever the amount of heat energy required by unit mass of a substance to change its state, as it is latent heat, it is changing from solid to liquid. If suppose if the substance is giving out the heat energy, then it is converting from liquid to the solid. That only we call that as latent heat of fusion. Okay. And in the same way, latent heat of vaporization means whatever the amount of heat energy it is taking while converting from the liquid to the gas. Or if the heat energy is given out, then whatever the amount of heat energy given out while converting its state, changing its state from gas to the liquid, in both cases we are taking for the same unit mass of a substance here. Okay, unit mass of a substance, where formula is L is equal to Q by M, L equal to Q by M, calorie per gram, that is. Okay. In the case of these latent heat capacities, if you are taking the example is we can take it for the case of ice. Okay. Latent heat of ice we can take, of which latent heat of fusion of ice, actually its value is 80 calories per gram, that is. Latent heat of fusion of ice 80 calories per gram, what is its meaning is 1 gram of ice requires 80 calories to melt. Okay. And here this melting takes place only at 0 degrees Celsius. Means if I am taking the ice at 0 degrees Celsius, it requires 80 calories there to convert into water, and even that water which is converted there, that also 80 calories required there taking, and its temperature is also 0 degrees Celsius, that is. Okay. So which means if you are taking 1 gram of ice at 0 degrees Celsius on supplying the heat of 80 calories, now it is becoming 1 gram of water. And again at what temperature means? At 0 degrees Celsius only. Because here 1 gram of ice at 0 degrees Celsius, okay, as there is no change of temperature here, because the heat energy given there, supplied there, actually it is given to the, not for increasing its kinetic energy, to change its potential energy, to change its state from ice to water. That's why no change in the temperature. So 0 degrees Celsius, 0 degrees Celsius. And that 0 degrees Celsius is nothing but the melting point of the ice we are taking. Okay. And in the same way, if you are taking 1 gram of water there, and again at 0 degrees Celsius, gives out 80 calories there to coming back to the ice, to convert back into the ice. Means just the reverse process. Now I am taking 1 gram of water at 0 degrees Celsius. Now it is becoming ice by giving out the heat energy of 80 calories here. Okay. This is the statement. Okay. So that's why here latent heat of fusion for ice is 80 calories per gram. This is its meaning. Okay. Now in the same way, now we are taking the next one, which is of latent heat of vaporization. If you are taking, means change of state, this time it is from liquid to gas or from gas to liquid, that is. If you are taking for that case, then latent heat of vaporization of water is equal to, actually that is 540 calories per gram, that is. Means each gram of water at 100 degrees Celsius, it needs 540 calories there to change its state from water to the steam in vapor state, that is. And in the same way, if you are taking 1 gram of steam there at 100 degrees Celsius, it gives out by each gram 540 calories there to convert back into the steam here, to convert back into the water there. Even that water is also again at 100 degrees Celsius, because there is no change of temperature here. For example, if you are taking that in an equation, then again 1 gram of water if you are taking at its boiling point, because latent heat vaporization takes place at boiling point, that is. So 1 gram of water at 100 degrees Celsius. Now by supplying 540 calories of heat, now it is becoming 1 gram of steam. At what temperature that is? Again 100 degrees Celsius, like this. Now in the same way, the reverse also we have to take the same, of which if you are taking the 1 gram of steam at 100 degrees Celsius, if you cool that, then it gives out 540 calories of heat again, and it is now becoming 1 gram of water at 100 degrees Celsius. And again if you observe, no change of temperature, 100 degrees Celsius, 100 degrees Celsius. This is the example. Okay. So latent heat of fusion of ice is 80 calories per gram, and latent heat of vaporization of water is 540 calories per gram, that is. Now we will see a numerical example on this latent heat of fusion and latent heat of water, that is. Okay. Numerical example means, for example, here I want 20 grams of ice. Okay. 20 grams of ice we are taking. Now what we need is, how much is the heat energy required by this 20 grams of ice, okay, to convert into water, that is. To convert to water. If you are taking this ice at 0 degrees Celsius, then water you are getting is also at 0 degrees Celsius. Water also at 0 degrees Celsius. And we know that as L is equal to Q by M, then amount of heat energy required, Q is equal to, it becomes M into L, that is. Q is equal to M into L. If Q is equal to M into L, here the latent heat is, as it is about change of state from solid to liquid, then we have to take here the latent heat of fusion, F, that is M into L, F. And here the mass given there, which is of 20 grams there, and latent heat of fusion, that is of given 80 calories per gram there. So 80 calories per gram, that grams get cancelled, and we are having 1600 calories there. Okay. The amount of heat energy we have to supply is 1600 calories, so that we can melt 20 grams of ice at 0 degrees Celsius into water at 0 degrees Celsius. And again the water we are getting, as the mass always remains the same, and here also we are getting the same, 20 grams of water we are getting there. Okay. And in the same way, if you are taking in reverse, means if you want to freeze some 20 grams of water at 0 degrees Celsius back into 20 grams of ice at 0 degrees Celsius, the amount of heat energy you have to given out, it has to given out is 1600 calories, that is. Okay. And in the same way, if you are taking for the case of water to the steam, but there the temperatures are different here, of which now we are taking 20 grams of water, but this time the temperature we are taking is 100 degrees Celsius we are taking. 20 grams of water at 100 degrees Celsius, now it is becoming 20 grams of steam, again at 100 degrees Celsius, like this. Then in this case, we are having latent heat of vaporization is coming. So that here the amount of heat energy we have to supply, Q is equal to again M into L, where L is, it's not latent heat of fusion. Now it is called latent heat of vaporization, that is. then m into where mass it is of 20 grams and latent heat of vaporization which is 540 calories per gram, that grams get cancelled, and 54 twos which is 108 and 2 zeros. Then how much required there is 10,800 calories. This is the amount of heat energy required by the water which is already at 100 degrees Celsius to become steam at 100 degrees Celsius. And in the same way, if you are taking that in the reverse, if you are taking 20 grams of steam at 100 degrees Celsius, now it is becoming water at 100 degrees Celsius by giving out the heat energy of 10,800 calories. So means in both the cases of taking boiling and as well as the condensation, we are taking the same latent heat capacity. Only thing is here the heat energy is given out, the other case the heat energy is taken. That is the only difference. Okay. Now we are taking both the specific heat capacity and latent heat capacity combined, and now we are seeing how to do the numerical problems. Okay. Now in that case, for example, we are taking of which we are having, let us say 10 grams of ice we have. This 10 grams of ice which is at 0 degrees Celsius is there. Now we want to vaporize this. We want to vaporize that. Means the question they will ask like this. So calculate the amount of heat energy required or supplied to vaporize 10 grams of ice at 0 degrees Celsius. Then actually what we have is 10 grams of ice at 0 degrees Celsius. But if you want to vaporize that, actually vaporization takes place at 100 degrees Celsius. Means at first we have to change this ice at 0 degrees Celsius there. And not only that, water at 100 degrees Celsius it actually vaporized to 100 degrees Celsius of steam there. But here we are having ice. So means we have to change the state also. So that's why first we are taking 10 grams of ice at 0 degrees Celsius. First we are converting this into water there. Means 10 grams of water at 0 degrees Celsius you will get. As here if you observe, there is a change of state is there, ice to water, and the temperature there 0 degrees Celsius, 0 degrees Celsius. No change of temperature that is. Let us suppose the amount of heat energy required there is Q1, whereas that Q1 is equal to m into L, where L means again here the latent heat of fusion we are taking, LF. Then mass is there 10 grams and latent heat of fusion which is of 80 calories per gram, that is 80 calories per gram. That grams get cancelled and here we are having 800 calories is present. Now this is for the amount of heat energy required for going from ice to water which is at 0 degrees Celsius. Now come to the next case which is of, now what I want is I want to vaporize that. If I want to vaporize that, the water has to be at 100 degrees Celsius, but here the water formed is at 0 degrees Celsius, which means we need to raise the temperature of the water. So that's why here that 10 grams of water, now I am taking at 0 degrees Celsius and I am raising that to 100 degrees Celsius, that is. Let it be the heat energy supplied here is Q2 is the heat energy. Okay. Then again Q2 is equal to, again if you see here the water you are taking, again water only, means first thing is there is no change of state. And another important thing is here 0 degrees Celsius, there it is becoming 100 degrees Celsius, means there is an increase in the temperature takes place. If there is an increase in the temperature is there, there is a requirement of heat energy is there. That heat energy Q2 is equal to, back to the specific heat formula which is Q equal to S into M into delta T, that is. If Q2 is equal to S into M into delta T, specific heat it is of, we already know as it is water 1 calorie per gram degree Celsius, and mass already given which is of 10 grams there into, and change of temperature from 0 to 100, 100 minus 0 which is of 100 degrees Celsius, that is the change. Okay, that grams get cancelled and calories also get cancelled. Finally we got 1000 calories. This is the amount of heat energy required while going from 0 to 100 degrees Celsius if you want to raise the temperature there. which is for Q2 case. Now, water is at 100 degrees Celsius and now it is ready to become steam if you supply the heat energy there. That is our third case. So, which means now 10 grams of water is now becoming 10 grams of steam, and again there is no change of temperature, because here there is a change of state takes place, water is becoming steam, then the temperature remains the same, 100 degrees Celsius equal to 100 degrees Celsius, that is. Okay. So, that is why in this case Q is equal to again formula M into L. Whereas the latent heat here we are taking is latent heat of vaporization, we have to take LV, that is latent heat of vaporization. Then it is equal to, here the mass given again, as there is no change of mass, always mass is same, 10 grams, and latent heat of vaporization, it is about, we are having 540 calories per gram. So, means 540 calories per gram, that grams get cancelled, then we are having 5400 calories, that is. This is the Q3 value. So, finally we got all the three heat energies there, which is first case for melting 1800 calories, and Q2 for change of temperature 1000 calories, and Q3 for again change of state from water to the steam 5400 calories. In total, if you add, the total amount of heat energy we supplied is Q1 plus Q2 plus Q3, that is, which is Q1 800 plus Q2 which is of 1000 becomes 1800 plus 5400. Okay. So, in total it becomes 0, 0 and 12, 6 plus 1, 7, 7200 calories. This is the amount of heat energy required. Q is equal to total 7200 calories. Like this, we can change from ice to vapor, and in the same way in reverse also the same procedure we have to take. So, finally we understood that here when there is a change of state takes place, we have to use Q is equal to M into L, where L is the latent heat capacity. When there is a change of temperature comes, again there we have to take specific heat capacity, Q is equal to Sm delta T. Now we will see a numerical example on the latent heat capacity. And along with the latent heat capacity and the specific heat capacity, we are having one more is there, that is called thermal capacity or heat capacity, that is thermal capacity, represent with C. Okay. So, thermal capacity means same as specific heat capacity, but here the mass we are not considering as unit here. We are taking the whole mass of the substance, means the amount of heat energy, required by whole mass of the substance to change its temperature by 1 degree Celsius. Okay. So, if you remember, the same definition we are having even for the case of specific heat also, but only difference is here. Here we are considering the whole mass of the substance, that specific heat we are not considering the whole mass of a substance, we are assuming that as a unit mass of a substance there. Here only the important thing we have to understand, that a specific heat capacity does not depend on the mass of the substance here. Okay? Because as we are assuming there the unit mass of a substance, for a given material, whatever the mass you can take, whatever the volume you can take, always we are having the specific heat capacity value remains the same. For example, if I am taking 1 liter of water, specific heat is same 1 calorie per gram degree Celsius. If you are taking 2 liters of water, then again same specific heat is 1 calorie per gram degree Celsius. But thermal capacity is not like that. It depends on the mass. Okay, for example, if you are taking 1 liter of water, thermal capacity is different. If you are taking 2 liters of water, thermal capacity different. So depending on the mass, this thermal capacity is varying, whereas specific heat capacity is independent of the mass variation here. Only depends on the nature of substance you are taking. Means the specific heat capacity remains the same until you change the substance. For a given substance, whatever the quantity you can take, always the specific heat capacity remains same. Okay. Now thermal capacity, actually formula, as it is depending on the mass, here we are having the formula is C is equal to Q by delta T, because we already took the mass here. For the whole mass of the substance, here I am taking the amount of heat energy there. That is why no need to write the mass here. So C is equal to, formula is Q by delta T, that is. If you are taking Q by M delta T, that is about the specific heat capacity, that is. So if you compare all the three thermal capacities here, latent heat, specific heat and this thermal capacity, if you compare, say for example like this, S, which is equal to Q by M delta T, and C, which is Q by delta T, and last one, which is of latent heat capacity, which is Q by M, like this. If there is no change of temperature, then specific heat, in place of that we are having latent heat capacity is coming. And if suppose if you are taking the whole mass of the substance, but there is a change of temperature is there, then specific heat is now becoming the thermal capacity here. Then if you check the units here, if it is of CGS unit you are taking, then it is of calorie per gram degree Celsius. This is calorie per degree Celsius and this is calorie per gram. Okay. And in the same way, if you are taking the case of SA system, then it is of joule per kg Kelvin, and here it is of joule per Kelvin, and here it is of joule per kg, that is like this. Okay. Joule per kg Kelvin, joule per Kelvin here and joule per kg, that is. And not only that, if you observe, we are having a relation between C and S is there. As S is equal to Q by M delta T, S is equal to Q by M delta T. But C is equal to Q by delta T there. This is 1 and this is 2. Then if you observe Q by delta T, here this part, that is nothing but C there. Then S is equal to, we can write that as this part is equal to C, C by M there. Then the relation between them, C is equal to M into S, that is. C is equal to M into S, that is. Okay. That is the relation between the thermal capacity and specific heat capacity. So if you want to find the specific heat capacity, then S is equal to C by M, that is. Okay. So that is about the latent heat capacities, specific heat capacity and thermal capacities, and these are about the change of states we have for different substances, that is. Okay. Now another important thing we have to see here is, during this change of states, sometimes the change of state occurs without taking the constant temperature of melting and boiling points here. In those cases, the effects are different here. Okay. Best example for that is the general condensation process takes place in our atmosphere, and not only that, we are having the process of evaporation there, evaporation and condensation, which is taking place at room temperature, that is. Okay. Let's say for example 40 degrees Celsius. Okay. Now we will see about that evaporation and condensation process. Okay. Now if you are taking the case of evaporation, evaporation is a case where here we are taking, there is a change of state takes place from liquid to gas. Actually liquid to gas, if you are taking in case of latent heat capacity, that it takes place only at boiling point or vaporization, that is. Yes or no, BP, that is boiling point, that is, which is at 100 degrees Celsius. But here this going from liquid to gas, which is called evaporation, it does not take that 100 degrees Celsius, it is below the 100 degrees Celsius. So that is why evaporation, what we will write is the process of change of state, change of state from liquid to gas at any temperature, you need not to take the temperature constant, at any temperature other than which should be strictly less than, other than boiling point. Okay, this is a definition. The process of change of state from liquid to gas at any temperature other than this boiling point, which is less than the boiling point. This process we call that as evaporation process. Most of the cases this evaporation process in our daily life, number of times we'll observe that. Best example is whenever after cleaning the floor with a wet cloth, if you on the fan, immediately after some time, after few minutes if you observe, there is no water is present on the ground. This happens because of due to evaporation process. And here there is no rise of temperature up to that boiling point here. Only in the atmospheric temperature only it takes place. The reason for that is whenever if you are taking the molecules which are present on the surface of the water you are taking, for example on the floor, here we are having that water particles are present. Now what happens there is these water particles which are moving in a different direction, random motion there. So both are colliding here, different particles are colliding here, particularly the particles which are present at the surface which are colliding with the particles which are present in the below there. These two both are colliding there, they are transferring their energy to the molecules which are present at the surface. Because of due to this what happens there is the molecules which are present on the surface, they are taking the heat energy there or they are taking the energy there and they are going to the excited state, which means they are changing their state, means from liquid to vapor like this. Okay, but once it enter into the air, enter into the atmosphere, in atmosphere we are having the dust particles are there or we are having air particles, different gases we have, then what happens there is these molecules which are present in the air, they are colliding with these particles. What happens there is again they are losing their energy and again they are getting down back into the ground here. Okay, and at the same time some cases what happens there is it remains still as a vapor here. If you are taking the area is more, then more number of molecules are having a chance to go as a vapor here. They are changing their state. Then we are having more chances of keeping in the vapor state only present. Okay, so that's why we say evaporation is a surface phenomenon, we'll tell. Okay, evaporation is a surface phenomenon, that is. Okay, depending on the area you are taking, more and more area you took, then more and more number of particles may vaporize here. So that's why evaporation is a surface phenomenon, that is. And not only that, if you observe the molecules which are present at the down, they are giving their energy to the other molecules to go up. So that's why these are losing their energy. As there is a decrease in the energy there, their kinetic energy there is a decrease in the temperature takes place for those molecules. So that's why evaporation is a cooling process. Okay, so mainly two things. Evaporation, actually it is of surface phenomenon, that is surface phenomenon, means having more area, more chance of evaporation, less area, less chance of evaporation, less probability there. Now, if you are taking that evaporation, not only that evaporation, it is a cooling process. It is a cooling process because the molecules are losing their heat energies here, losing their energies here, their kinetic energy is there. Due to that, the result is there is a decrease in the temperature takes place. That's why it is a cooling effect, that is. Okay, so this is about the case of evaporation. This evaporation, not only in case of these floats, we can see whenever if you are taking the wet cloths outside, whenever if you stretch the cloth there in the summer days or in the hot days or daytime there, then what happens there is whenever if you stretch, the area is increasing so that it is getting evaporated, it becomes dry very quickly there. And not only that, when you are drinking any of the hot drink there like tea or coffee or milk there, whenever if you are taking that into a cup or into a dish or into a saucer there, where we are having more area is present like saucer, immediately that is cooling down very fast. That is because of due to evaporation is a surface phenomenon, and not only that, that is a cooling process that is. So, that is the case of evaporation, which is a cooling process. Now, we are seeing in the reverse, which is of even the condensation process also takes place in our atmosphere, that is. Condensation process taking place in the atmosphere means that is converting gas back to the liquid. How that is possible is, in the atmosphere, here what happens there is the molecules which are in the vapor state, particularly if you see humidity there, the vapor particles which are present in the atmosphere. So, whenever if you are taking any of the cold body, for example, like we can take a cool drink bottle. When you are taking a cool drink bottle outside there in atmosphere, if you keep around that cool drink bottle, now you will see small water droplets are present. Those water droplets are coming because of due to this condensation process. And this condensation is not like latent heat case. This condensation takes place at room temperature, that is. Whenever if you are taking that bottle which is of cold water, if you are taking inside, or cool drink bottle if you are taking, which is a closed one, around that if you are exposed to the atmosphere, this one, around that cold body here you will see water droplets are coming on that. These water droplets are coming because of due to, as this is a cold body, around that air we are having vapor particles are present. Those vapor particles which are in the excited state, they are having a cold body is present, then heat transfer from hot body to cold body, then what happens there is it is changing its state from gas to the liquid, and that liquid water droplets they are forming on the surface of the cool drink bottle here. The same thing we will observe in the winter, some winter days there, on the car headlights or the car glasses or at windows, particularly on the leaves of the trees, we will observe this condensation process. And the reason for in winter season, particularly this fog, or you can take for the case of dew, this dew and fog, these are also coming from condensation process only. For example, if you are taking the fog which is acting like a thin mist here in the atmosphere, in the air, how that is formed is, these vapor particles after getting cooled down here, they are forming onto the dust particles here, the air molecules. So that what happens there is, along with those air molecules here, these dust particles also floating. As they are floating on the dust particles there, they appears to be like a thin mist, like a blanket, so that we cannot see in the daytime very clearly this any of the road there. That's why we have to use a separate lights for that. We call that as fog lights. Okay. And in the same way, dew you will see this like this, it happens on any of the cold surface. Okay. So from the from the air, the vapor particles are converting into the liquid form here because of due to cold body. Okay. So till now we will cover all these latent heat capacities there, thermal capacities there, and how to do the numericals, and how these general cases of evaporation and how the process of condensation takes place.